So the talk is on convergence of big data and HPC and why it's so inevitable, and try to give you some sense of what are the technological impediments and how we are trying to solve them for the future in our many multitude research we do ourselves and some research we do with DDN. Right now we have a supercomputer called Salami, now 2.5, incarnation 2.5. You can think of this as a computer that has a similar capability to K computer. It's got 17 petaflops single precision performance, 6 petaflops double. It's 13th on the top 500 list, just announced. It's also got 7 petabytes of DDN storage. We have Lustre GPFS. I think I talked about the machine to detail and previous presentations for DDN, so I won't really go into details on this. So right now we are preparing our next generation machine, Salami 3, to be commissioned in around 2016. It'll be a 22, 30 petaflop machine. But the emphasis is really not on just things like compute power and also green computing, which is also very important. I have a separate talk this afternoon on how we are experimenting with green, being very efficient in terms of power consumption. We are really trying to push forward very high I/O capabilities and the middleware to be able to exploit those. So why is that? Well, because we believe that big data, as important as it is to society, there's a real, when I go ask for a layman, for example, I ask a newspaper reporter, he asked me something on big data, and I ask him, what's big data? And they say, well, big data is about, this marketing. So the real definition of big data today for many people is mining people's privacy data to make money. And that's because corporate data is typically used for things like marketing or maybe basically what humans produce, which is actually not huge in volume. It's very, the data volume and the processing complexity is really somewhat lightweight. And that's why things like Hadoop have proliferated, because you can do this in a lightweight repurposed web servers running Hadoop HDFS, which runs on Java, of all things. And so that's the state of the art. But many people predict, including us people working in the scientific arena, that when corporate silos break down and there's massive amounts of data, the current infrastructure will be just overwhelmed, and thus will require supercomputing power in data, and thus we need extreme big data computing. Just to give you a few examples, this is a metagenomics example that's being done by a team of people, including Professor Akiyama at Tokyo Institute of Technology. So the idea is to take a whole bunch of genomes from the environment, like sea, soil, maybe your gut, which will also include your own genes. But because these metagenomics is really sequencing the genes in a biosphere, not just single organisms, but it tries to identify the metabolic pathways by which these multiple organisms exist in order to create this ecosystem, and that creates a certain phenomena. For example, you have a biosphere in your mouth. And why does somebody have a bad breath? Why do some people get gum disease? Well, it cannot be told without really studying the ecosystem of both the bacteria and also what's, you yourself, what's contained in the saliva, just also the human genes. So what they have done is to sample the genes from, stuff from various parts of your mouth, and do the whole sequence analysis, and they have to do these affinity calculations using the entire K computer. Now, K computer is very big. It's got over a petabyte of memory. It's got 600,000 cores. It took them the entire K computer to do this, essentially is a big data analysis. And they've been able to identify that there is a certain metabolic pathway, and these are categorized into different parts of your mouth, which is actually quite a bit of a medical breakthrough. And so, but this is a very typical, this is just one instance of a science that's being done today in so-called big data that basically would be using the entire machine of some of the biggest machines in the world. Similarly with graph processing, we got from anywhere from road networks to like human brains. But when you're trying to do analysis of human brain, there's a European Human Brains project, which I am kind of peripherally involved in. It's got, human brain has about 90 billion nodes and 100 trillion edges. You can model your human brain like that. Even large social networks, when you try to study correlation between social networks, it results in this humongous graph. So can existing infrastructure solve this? Well, the Graph 500, which was announced yesterday, is a so-called big data benchmark. And when it was in its inception, one of the inventors, Rich Murphy, claimed that there's an expectation that this ranking may look very different from the top 500. In fact, if you could envision something like cloud infrastructure being part of being ranked very high and be a major portion of the ranking. The reality is that when you look at the Graph 500 results today, there are no clouds. There are no clouds in this ranking. So why is that? Why, you're doing, clouds are doing big data. You have Google's and Amazon's doing big data. Why isn't the Graph 500 results? Google does sorting, but it's not here. Why? Well, it's not in the Graph 500. Why is that? Well, when you think of big machines like a K computer or the IBM Blue Gene Q, or like the #1 machine in the world, Tianhe 2, these have tremendous number of cores. K computer, like I said, has several hundred thousand cores, about 800,000 cores. Blue Gene Q, Sequoia, has about 1.6 million cores, and then the Tianhe 2 has about 3 million cores. And when you think of large IT companies that have large infrastructures like Amazon, there are lots of speculations as to how much resource they have. Well, one theory, when you do the inverse analysis from what the analysts at IDC or Gartner, those people, the data they provide, we can kind of guesstimate that Amazon may have about something like 500,000 nodes. But because these are using commodity servers, the core counts are low. So you can think of Amazon having aimed from like 6 or maybe higher, maybe 8 billion, I don't know, up to maybe 10 million cores. But when you have 6 million, say you have 6 to 10 million cores, it's not so different from Tianhe 2. Tianhe 2 has 3 million cores. So a single supercomputer has a capacity which may not exceed the existing likes of Amazon. Well, Google may have about twice or 3 times that. But when you think of the DARPA study, which predicts that the exascale machine has 100 million cores in 2020 or 2022. So will Amazon or Google have 100 million cores in 2022? Well, that's highly unlikely. And also, when you connect, more importantly, things like graph processing is heavily bound by the interconnect speed. So when you look at our machine, again, Salami 2, the interconnect bisectional bandwidth is about 220 terabits. So you can see, using most advanced silicon photonics at the time in 2010, you can see it's a jumble of fibers. We got about 100 kilometers of fiber just bunched up in this really, really small space. And a lot of people brag about having large data centers. They got huge data centers. We got tens of thousands of feet of floor space. But in reality, when you look at them, they're really sparse. Where they're sparse, well, they may not need so much networking. So they can afford to place these data centers to be sparse and not densely built like supercomputers. But when you look at the bisectional bandwidth of these data centers that are more classically built, they have top-of-rack switches. They do gigabit to 10 gigabit, well, nowadays 40 gigabit aggregation and so forth. But looking at the real data center, well, some data centers are changing nowadays, but a typical data center, there's like a factor of 1,000 difference in bisectional bandwidth. So they may have hundreds of gigabits in the bisection, but it's nothing compared to supercomputers. So, and in fact, what does 200 terabits mean? So this is the figure announced by Cisco saying that the global internet traffic is about 2014, about 69 exabytes per month. But when you do the division, which may sound like a lot, this is in the backbone, but when you do the division to calculate the average bandwidth of the internet, it turns out to be it's about 200 terabits per second. That number looks familiar, right? 200 terabits per second. So a supercomputer that we built, which is, well, number 13 in the world, has the bandwidth capacity that matches the average backbone internet traffic of the world. So, and data centers are built to serve this traffic, but all the data centers of the world. So there's just no match that supercomputers, the power they provide, as opposed to how data centers are built today. So that's why we're set about to do the research and also to deploy, try to do, ultimately deploy the technologies, the infrastructures for next generation data, which are coining as extreme big data, which kind of seem a little redundant. But big data is already taken, so we got to say something that's more extreme. So really to think about how do these conversions happen? How do cloud IDC technologies and supercomputing technologies, how can they be converged into a more coherent infrastructure and have both a hardware design, software stack, libraries, languages, and how they would, and we would try to investigate this using co-design with a very typical extreme big data applications that are known today, such as large-scale metagenomics I mentioned, or like real-time weather simulation. This is very, very difficult problem. Or ultra-large graph processing, things like extreme large social networks and brains and so forth. And we're not just doing this, so I have my project, but we're not doing this alone. There are several affiliate projects that we're all collaborating within Japan. And so there are about 5, 6 projects. Each is doing its own part of the job in order to design and build the technologies and infrastructure for the next generation of big data. So one instance of this is, so as a testbed, there are various testbeds we use. One testbed using is what's called salami KFC, which is a prototype for the salami 3 machine that we're going to, like I said, we'll build in 2016. And this already on the compute side has became the greenest supercomputer in the world, winning the Green 500 last November. We'll see how we'll do this time for this Green 500. But we're also adding storage in terms of very larger capacity solid-state drives that'll give us a local bandwidth of about 50 terabytes of capacity, or about 50 gigabytes per second of bandwidth for a single rack, which is, if you do the math, suppose you have 40 racks of this, it'll give us several terabytes per second of bandwidth, aggregate bandwidth. And we're trying to push, by the way, KFC means Kepler fluid cooling, nothing to do with certain American chain. Although the machine is soaked in oil, and salami, as you can see, is a bird. There's no relevance here. And we're trying to be more aggressive design in order to have a lot more higher capacity I/O, how we can embed these higher capacity flash devices and non-volatile memory devices into the box, and whether we can utilize them. What's the right low-level system software, and we've been able to successfully put in a single node something about almost like 8 gigabytes per second using very, very cheap devices. And so this is for 2016 exercise, but we're very happy that we're getting, if this technology will scale, even at this point, we can get 10 terabytes per second I/O bandwidth, which will actually set. And when you can do the calculation, will actually almost saturate the Tsunami's network, which I showed you moments ago. And we can even go beyond. We'll try to go beyond that. As for the algorithms, so what are the algorithms that can we run on these? So we have a collaboration with Professor Fujisawa's team. So they're mainly working on graph algorithms in their project, and we're collaborating with them to see how the graph algorithms will be applicable to machines with such kind of non-volatile storage down below. So you have a very deep memory hierarchy. how do graph algorithms work? How can we offload much of the graphs onto the slower non-volatile memory? So we've been very successful. The combined team have been very successful in terms of devising the fastest graph processing algorithm in the world. In fact, what's been so this is just in a K computer. These are results not using non-volatile memory, but the baseline algorithm not using volatile memory actually it was just announced yesterday that on a K computer it became the fastest graph algorithm in the world by being ranked number one in the world. So here are happy faces of the team. Number one. Yeah, it's the first time that the Japanese supercomputer became number one on the Graph 500. And based on the observation from those achievements, then we are also continuing working in parallel to try, like I said, to try to offload the graphs onto the SSDs. So, but by offloading, we don't want to lose performance. So we're doing various analysis for both from the algorithm side, also statistically analyzing what parts of the graph are accessed more frequently, what part of the graphs are not accessed as much, in order to offload the graphs as much as possible onto these non-volatile memory. And some of the preliminary results we had is we can get like 7% offload much of the graph without much degradation. So we can handle graphs that are 4 times as big as will fit in your DRAM, but still only suffer about 7% performance loss. So we've been using these algorithms. So the last this is what's called a green graph 500, which gives you the energy efficiency of graph processing when you're doing the graph 500. And the last graph 500, green graph 500, in the big data category, I won't go into details how these are distinguished, was also won by Tsubame KFC. So if you and the metric for this is measured in terms of megateps per watt, is how much traversals, edge traversals you can do in per watt on average, or how many edge traversals you can do in a single joule. And we beat BlueGene, which was about 20% last time. But then we really tuned some of the algorithm for doing graph offload onto to these flash devices, and we got about 6 times better power performance compared to this number one machine, the KFC. So by being able to use smaller processing devices, but much bigger memory capacity, as provided by this very deep hierarchy using flash devices, we were able to greatly reduce the power consumption requirements and thus be able to achieve this power efficiency. Now, fortunately, this came in number 3 because we had another algorithm running on DRAM-only machine, which dealt with smaller graphs but was more power efficient. So we beat ourselves using our own algorithm, but that's still fine. Because these numbers are really important. Other algorithms like sorting. So sorting is very important. Like when you have Hadoop, you do sorting in between. But how can you do very fast sorting on a supercomputer? Utilizing the networks and also very fast bandwidth, for example, afforded on devices like GPUs and Xeon Phis. And what are the flexibilities sorting? Is it a fixed length key sorting? Is it variable key length sorting? What are the sorting algorithms that are more efficient? Is it merge sort? Is it sort of like a quick sort? Is it hybrid sort? There are various studies that are going on, but we still feel that people have not maximized the power of the supercomputers or the power of the devices embedded in these supercomputers. So we've been able to achieve very good results and also derive various performance estimates. This is a result of a variable length key sorting, which is typically used in genomics. So we have, this is sorting strings with variable length. So it's a much harder problem than sorting with that are fixed length. But we get very good results on accelerators like GPUs and Xeon Phis, twice as fast as CPUs. And this is a result of, this is fixed length sorting, but we'll try to make it as scalable as possible. And we're able to achieve about a factor of 400 using very large scale GPU machines. And, but unfortunately, right now, our performance model and our measurements say that the PCI Express bandwidth is a bottleneck. But we have performance predictions based on the existing data and also the modeling of the cost of sorting, which says that when next generation interconnects between GPUs or CPUs come into play, like the NVLink has been announced by NVIDIA, then what happens is this elimination of this bottleneck, we can get fantastic speed ups in sorting. In fact, some numbers indicate we are order of magnitude faster than some of the most recent results that Google has with their sorting benchmarks. So again, yeah. I can be fine. Okay, another 5 minutes. And then abstractions. How do we let people use them? So there are existing abstractions. There are new abstractions we need to let people program. So existing abstractions like MapReduce, which is important, but it's also important that we design MapReduce systems that utilize accelerators like GPUs, again, affording high bandwidth, and also being able to utilize these non-volatile memory devices. The key here is how to, again, control the memory hierarchy and how to hide the latency inherent in transfer, because you have slower devices on the bottom, you have faster devices on the top. So Hammer is our new implementation of MapReduce that tries to utilize the underlying hierarchy system to use the most optimal algorithm as much as possible, and also adapt to the various differences in terms of the speed, and as much as possible use latency hiding and other techniques in order to overlap the computation and communication to achieve the optimal. So, so we have GPU-based key handling algorithm to make sure that it's as fast as possible. We overlap computation of GPUs and CPUs in order to hide the latency, and we use out-of-core GPU sorting algorithms so we're not constrained by the size of the GPU memory. Again, we have some real good numbers here. Again, we're somewhat constrained by the PCI Express bandwidth limitation, which we expect will go away pretty soon. But we do get, well, even so, we get significant speed up compared to CPU-only solution, factor of 2 or even greater in some benchmarks when we utilize GPUs to these problems, which are already fast, this is already very optimized MapReduce system, but having GPUs, we go much faster. Similarly for graphs, now we're building a graph library. I don't have much time, but this is a scalable graph library running on very big machines, and that allows us to process graphs that consist of billions of edges and apply the latest graph processing techniques. I'm sorry, I skip over some of the details due to the lack of time. Finally, we need to be able to allow people to use these capabilities in hardware, the hardware capabilities in terms of things like being able to support resilience using these types of high bandwidth I/O. And we have worked with Livermore in trying to model burst buffer, next generation burst buffers. And burst buffers are utilized to, in the past, had been proposed to basically try to smooth out the I/O. Now it's being regarded as a key technology to basically increase the reliability in the system by having very fast checkpoints, or trying to alleviate I/O bottlenecks of applications by making them be more this I/O processing engine rather than just being a temporary storage. But the question is, what are their characteristics? We don't really understand how burst buffers work. I mean, how should we design them? What's the design point? What are the right system software in order to be able to really make these burst buffers perform fast? What happens if burst buffers break down? Because you're trying to, for example, if you're trying to use burst buffers for checkpointing, but if burst buffer breaks down, what happens? What are the reliability characteristics? These are all the things we don't really know. So we've been designing both the system level, very fast I/O for burst buffers as a system level work, but also trying to model the burst buffer characteristics so as to know what are the resiliency characteristics, what are the performance characteristics, given a burst buffer configuration. I really won't go into the details of the model. Basically, we have a hierarchical model that we can construct these burst we can describe these burst buffers in a very constructive way in a hierarchical fashion, and then we can consider this as a basically probabilistic model, hierarchical probabilistic model that's an extension of the work that was done at Livermore. So basically, it's a multi-level Markov chain. In order to come to the probabilistic assumption of how, for example, how reliable these are on the given a certain configuration. So we've done lots of analysis in terms of the I/O performance, and also what are the resiliency characteristics. For example, in the exascale era, will these burst buffers allow us to make our system reliable enough in the presence of frequent failures? Well, without going into details, the answer is yes. And well, yes and no. If we design these things right, it'll have sufficient characteristics so as to be able to make our system reliable. So even if it's subject to fairly frequent failures, like in matters of 20 minutes, our simulation model says yes. Well, we can get reliable performance. But if we grow a system any bigger, factor 10 beyond exascale, then everything falls down. So then we have some problems there. Also, we get a very good, very high bandwidth on this burst buffer I/O on a system level, and these kinds of very fast direct I/O from the network onto these storage class memory devices is going to be a key in terms of the next generation system softwares for extreme big data processing. I'll skip over some of this and come to a conclusion because we ran out of time. So we believe, and in the future, so all of this is being done not just with SPAME 3, but for the future. And we believe in the 2020, 21, 22 timeframe, next generation of machines, we believe that the convergent architecture can be really small. It will have MB RAM, just like what HP announced recently with their the machine. We have a very similar concept. And some of the modeling we've done, rudimentary modeling we've done, we believe we can build something like, almost like 1,000, 1/500 to 1,000 the size of K computer, with 1/500 the cost, and we'll have 5 times more memory capacity in a single rack. And so thus we can replace this gigantic data center with a single box in 2020 if we assemble all the technologies that are described to you and even more, and plus what other people are doing, that allows us to even replace data centers themselves. So our hope is that data center will be in a box. And so large data center, people who brag about large data centers will become Jurassic. And that's what our hope, and that's what we'd like to achieve in the next 10 years. Thank you.